class, we are starting chapter 21, and I'm going to briefly go over chapter 21.1 and 22.2. So this is, I'm going to skip over the appendicitis. Let's go straight into understanding what we're looking at. Nuclear reactions are different than chemical reactions. So everything that we've learned up to this point will help understanding this, but we are going to look at this in a different way. Chemical reactions affect electron configurations and the bonds. Physical processes affect intermolecular forces. Nuclear changes in most cases alter the number of protons in the nucleus of the atom. So we are dealing with protons, and where we have learned in the past to deal with electrons. So when we deal with protons, which is how we're going to look at nuclear reactions, that also changes the atomic number. So it's going to change an element. So before, what we learned with balancing is it's the same atom, it's the same element. That is all out the window now. I know you're not going to believe me, but it should not be as difficult when you first learn that, if you can remember when you first had to learn all of that stuff. But it is different. So we are dealing with protons, which changing a proton means changing the element. That is what a nuclear transmutation means. So nuclear reactions differ from chemical reactions, and we can look at this. So chemical reactions involve electrons, which means that you make and break bonds. The atomic numbers do not change. So whatever you have on one side of the reactant, you have on the other side where the product is. Isotopes of a given element behave almost identically. Remember what isotopes are. They have different neutrons, but they are the same element, same proton. The total quantity of matter does not change. Okay, so different. Now we are handling things a little differently. This involves protons and neutrons. Atomic numbers almost always change. Why is that? Because almost all of these involve changing the protons. And if we change the protons, that means that changing the element or the atom also changes with it, goes hand in hand. Different isotopes of an element will behave differently now. And a small amount of matter is converted to energy. And that's what a lot of people don't understand with this, nuclear reactions. It's a very tiny amount that causes such an immense impact. So this is from I teach another class, and I broke it down for that class. So this is pretty much the same thing, but a little bit more in detail. For chemical reactions, a substance is converted into another, but the atoms never change identity. Electrons are involved as bonds break and form. Nuclear particles do not take part in that. So that's nuclear particles, protons and neutrons. Reactions are accompanied by relatively small changes in energy and no changes in mass. Remember the law of mass reaction? Constant composition. The mass on one side does not change the mass of the other side. It's all constant. Nothing is neither created nor destroyed. Reaction rates are influenced by temp, concentration, pressure, or catalyst. For nuclear reactions, atoms of one element typically convert into atoms of another element. Protons and neutrons and other particles are involved. We're going to discuss what those other particles are. Electrons do not participate as much. They are in one portion, but really we're looking at other things here. Reactions are accompanied by relatively large changes in energy and measurable changes in mass. And reaction rates depend on the number of nuclei, but are not affected by temp, catalyst, concentrations, or pressure. So basically what you've learned up to this point will help you understand it, but we're not going to use that information, if that makes sense. So important terms in nuclear chemistry, these things are going to come up. Recall that isotopes of an element are atoms that have the same number of protons, but different neutrons. Isotopes of an element have the same atomic number and nuclear charge, but different mass numbers. So we're going to cover this in the next section. Symbols for isotopes can include both Z and A. So remember, we use these letters to match up for what we want them to be. So Z is nuclear charge, A is mass. So that's what those symbolize. So, and how to write these out. So I'm going to show you this. You'll probably see this slide again. But we're going to have to do a little bit of a review because you probably don't remember that this is how you are. This is the mass number. This is the atomic number for cobalt. So these are some of the things this is how you know you're dealing with isotopes. They look a little different because the mass number is included and so forth. Isotopes refer to the entire atom, including electrons, while the term nuclide refers specifically to the nucleus of the isotope. So these are some terms and a little bit of a review. So radioactive decay. The radioactive decay is simply Emission of a subatomic particles, so remember subatomic particles are inside the atom, or high energy electromagnetic radiation by the nuclei of the center atoms. So the nuclei of some naturally occurring isotopes spontaneously alter their number of protons and neutrons to become more stable. That's the whole thing. Remember I told you in chemistry, everything has got to be, goes to the lowest energy, which is the most stable. So some things are not, some isotopes, they're not stable and they're trying to get stable. And in the process of doing that, they release their, energy or particles, subatomic particles, in order to become more stable. Thereby they become another atom or element. This process is called radioactive decay or nuclear decay. Isotopes that decay are considered to be radioactive because they emit radiation, nuclear radiation, and they consist of particles and energy, which we will cover in another section. Because of the release of particles, this occurs spontaneously. It is recurred to natural radioactivity. So nothing sets that off. It just happens, and we've already covered spontaneous reactions. So basically, the overall, anything that is called radioactive, it is something, the atoms emit radiation. So if it emits radiation, it is called radioactive. This is used in, we're going to cover this in the last section, various applications. So radioactivity has numerous applications for diagnosis and treatment of medical conditions. I'll discuss this picture that I put up. This is not in your book. I took this picture from another slide that I teach for another chemistry class. Most radioactive emissions can pass through body types. We're also going to cover that. And what types of radiation can pass and how far, because most people don't understand radioactivity, and different types of radioactive particles travel different distances. Naturally occurring radioactivity is used to estimate the age of fossils and so forth. Radioactivity led to the discovery of nuclear fission. And so there's just so many things, applications. When you hear radioactive, you really don't understand that there's a lot of stuff that goes on with this. So what is this picture about? This picture, and I put this up on purpose because men should definitely have their prostate checked. And I know I have friends that are very hesitant to do this stuff. And I've had family members that have had prostate cancer. So what is this picture? So I'm putting this up. And so as you can see, this probe goes in and you see what these little, they call these like seeds. They're little seeds. So it's an implantation of a titanium capsule. So they call them the seeds pretty much, in the malignant area. And the radiation from these seeds destroy the cancer by interfering with the reproduction of cancer cells. And they do minimal damage to the adjacent normal cells. So this is an interesting, I actually found a live picture of a view, not directly in, but it was an interesting picture, and I decided that might be too graphic, so I didn't put that up. So I put this one up. This is for any, if you know males, push them to get checked with prostate for their prostate. That's all I'm saying. Okay, so let's jump into phosphorus. Phosphorus is I know I'm not saying this name right. I even tried to look up the how to say his name, and I didn't really get anywhere. And so I'm going to call it Becquerel, but I know he is, I think, French. So I am not doing justice to his name. He was doing some experiments, and he was looking into phosphorescent minerals that give off X-rays. Phosphorescence is very related. It's related to fluorescence. However, it lasts longer, so it has a longer time scale. So the emission actually occurs well after excitation ceases. So this is what you see, like the glow in the dark stuff. Basically, he was looking for something, and it turned out that what he thought was happening was not happening. I'm just going to leave it at that. And what he did discover by looking at these crystals that he thought were being phosphorized, it turns out they were actually giving off rays, and he discovered that uranium was responsible for this emission of these, what he called uranic rays, and that's what started looking into this radioactivity. So, and that he started doing that in 1896, and along comes Marie Curie, who is just this pioneer, and over here, she's got an interesting life. Amazon Prime has a story about her, did a movie. It came out last year and I watched it. It's very good. I unfortunately do not remember the name of it, but if anybody wants to know, I could look it up. It's very interesting because she was extremely smart, and she married her husband, who ended up doing research. He was more of a physics person, and her research is still so radioactive today that it's got to be locked away because it just gives off. Her husband ended up dying from the effects of all of this. Her daughter also went into chemistry, so her daughter also, I believe, won a Nobel Prize. So Marie Curie won 2 Nobel Prizes with the work of her husband, and then one by herself, I think. And her daughter Irene also went into chemistry and won a Nobel Prize. So it's fascinating. She went to the Sorbonne, which is in Paris. So when I went to Paris, I took a picture of it because I knew she went there. I thought it was cool. So yeah, her stuff is still so radioactive.